Imagine being stretched like spaghetti, atom by atom, as you cross into a black hole's grasp. Your feet would accelerate faster than your head, pulling you apart with unimaginable force. This isn't science fiction, it's a real phenomenon called spaghettification, and astronomers consider it one of the most violent deaths in the universe. What's more terrifying? We've actually observed this happen to stars, like in 2020 when astronomers documented a star being torn apart by a supermassive black hole 215 million light years away. But to understand why this happens, we need to examine a fundamental question about gravity itself, a force we think we understand until we encounter its most extreme manifestation. The physics of tidal forces. Gravity isn't as simple as we might think. What if this force could pull different parts of your body at different strengths? This isn't some bizarre science fiction concept. It's happening too right now, though the effect is so minimal you'd never notice. On Earth, gravity pulls slightly harder on your feet than on your head, specifically about 0.006 cm/s superscript. Too stronger, but the difference is too small to perceive. Yet this same principle, amplified millions of times, explains why objects near black holes don't simply fall in whole. They get stretched into long, thin strands. This stretching effect comes from what physicists call tidal forces. The name originates from the most visible example on Earth, ocean tides. When the moon's gravity pulls on our oceans, it pulls slightly harder on the side of Earth facing the moon than on the opposite side. This difference creates a bulge in the ocean on both the near and far sides of the planet, causing the daily rise and fall of tides. Tidal forces emerge from a fundamental property of gravity. It weakens rapidly with distance. Gravity weakens rapidly with distance. Double the distance and gravity drops by 4. So near a black hole, the pull difference between your head and feet can surge from imperceptible to utterly destructive. This rapid weakening with distance means that even small differences in position create measurable differences in gravitational pull. For everyday objects on Earth, these differential forces are negligible. The difference in gravitational pull between your head and feet is only about 1 part in a million. But near a black hole, these differences become extreme. A black hole concentrates enormous mass into an incredibly small space, creating a gravitational gradient so steep that the pull can vary dramatically over tiny distances. Consider what happens as an object approaches a stellar mass black hole. At 10,000 kilometers away, the difference in gravity between the front and back of a 1-meter object might be minimal. But at 1,000 kilometers, that difference grows significantly. By 100 kilometers, the front experiences substantially stronger gravity than the back. This creates a stretching force along the radial direction toward the black hole. This is where the physics gets truly extreme. The mathematics of general relativity shows that as you approach the black hole, these tidal forces increase with the inverse cube of the distance. This means having your distance to a black hole increases the stretching force by 8 times. The strength of these forces grows so rapidly that they quickly overcome the internal molecular and atomic bonds that hold matter together. What's fascinating is that the same gentle force that creates the rise and fall of Earth's oceans becomes catastrophically destructive near a black hole. At a certain distance, what astronomers sometimes call the spaghettification radius, the tidal forces become strong enough to overcome the electromagnetic forces that hold molecules together. Even the strongest materials in the universe cannot withstand this stretching. The gradient of force across an approaching object creates a distinct pattern of destruction. It's not simply a case of being pulled apart in all directions. Instead, objects elongate dramatically along the radial direction pointing toward the black hole while simultaneously compressing in the perpendicular directions. This creates the distinctive noodle-like shape that inspired the term spaghettification. But why do objects stretch rather than simply getting crushed? This question reveals something counterintuitive about how gravity works near black holes. The stretching occurs because the gravitational pull on the front of an object is significantly stronger than on the back. The front accelerates faster toward the black hole than the back can keep up, causing the object to elongate. Meanwhile, from the sides, matter gets squeezed inward toward this lengthening central axis. To visualize this, imagine holding a rubber ball near a black hole. The side closest to the black hole would accelerate faster than the far side, stretching the ball into an oval. As it gets closer, this oval would elongate into a thin strand, all while compressing from the sides. This isn't crushing in the conventional sense. It's a directional redistribution of matter. The physics behind this process operates at all scales, from human-sized objects to entire stars. The critical factor is not the size of the object, but the gradient of the gravitational field across its dimensions. Larger objects actually begin experiencing significant tidal effects farther from a black hole because there's more distance between their front and back sides, creating a greater differential in the gravitational force. At the atomic level, these tidal forces affect matter in particularly violent ways. First, bonds break, then atoms deform, and finally, nuclei can split when tidal acceleration exceeds atomic binding forces. This material forms a long stream that astronomers call a tidal tail, essentially a river of atoms flowing toward the black hole. The process continues until the entire object has been reduced to this atomic stream. What makes this particularly unsettling from a physics perspective is that these forces are inescapable. Unlike other destructive forces in the universe, tidal disruption doesn't depend on the composition of the object. Whether you're made of steel, diamond, or flesh, the physical outcome is ultimately the same: complete structural failure and transformation into a stream of elementary particles. The mathematics predicting this process has been verified by astronomical observations. When stars pass too close to supermassive black holes, astronomers observe precisely this kind of tidal disruption. The star doesn't simply vanish into the black hole. It gets stretched into a long arc of stellar material, with some flung outward in spectacular displays, while the rest feeds into the black hole. Understanding these tidal forces gives us insight into what would happen to any matter that ventures too close to a black hole. But what would this process feel like for a human body? How quickly would our biological structures fail under these extreme conditions? The answers reveal a fate more terrifying than almost any other in the universe: the human experience of spaghettification. To comprehend the physical reality of this phenomenon, let's follow a specific scenario. You're in a spacecraft that's malfunctioned, sending you on an irreversible trajectory toward a stellar mass black hole. A black hole with roughly the mass of our sun. What would your final moments actually feel like as tidal forces begin to take hold of your body? Your first physical sensation would occur while you're still relatively far from the black hole. At about 10,000 kilometers out, you'd notice a strange pulling sensation. Your feet, being closer to the black hole than your head, would experience slightly stronger gravity. This difference might feel similar to the sensation of blood rushing to your feet when standing up too quickly, but gradually intensifying. As your spacecraft continues its fatal approach, reaching about 1,000 kilometers from the black hole, this pulling sensation would transform into genuine discomfort. The differential gravity would now be strong enough that you'd feel a distinct stretching sensation along your body. Your internal organs would begin shifting downward, creating pressure on your lower abdomen. Blood would flow more readily towards your feet, while your heart would need to work harder to pump it back upward against the increasing gravitational gradient. By the time you reach 500 kilometers, the gravitational difference between your head and feet would become severe enough to cause genuine pain. Your joints would begin to stretch beyond their normal range of motion. The connective tissues in your ankles, knees, and hips would experience strain comparable to having several people pulling on your legs while others hold your torso in place. The sensation would be similar to the most extreme stretching you've ever experienced, multiplied many times over. At approximately 300 kilometers from the black hole, the tidal forces would exceed what human connective tissue can withstand. According to calculations based on the strength of human ligaments and tendons, the differential acceleration between your head and feet would reach about 500 times Earth's gravity at this point. This means your feet would be pulling away from your body with a force equivalent to having several tons attached to them. Your ankle joints would be the first to fail, followed rapidly by your knees and hips. However, your body wouldn't simply snap at the joints. The gravitational gradient affects every part of you continuously, not just the connection points. Your muscles and skin would stretch like taffy, blood vessels would elongate and rupture, and your entire lower body would begin to stream downward toward the black hole. This process would accelerate quickly as the distance decreases. By 200 kilometers, your circulatory system would completely fail. Blood would be forcibly pulled toward your lower extremities, preventing return flow to the heart and brain. You would lose consciousness from the equivalent of extreme vertical G-forces. This circulatory and neural failure would occur before the most extreme physical destruction begins. At around 150 kilometers, your body's structural integrity would completely fail. Rather than remaining as a cohesive organism, you would begin transforming into a vertical stream of biological material. At approximately 100 kilometers from a stellar mass black hole, NASA's space math calculations show the tidal forces reach about 51,700 times Earth's gravity. At this point, the process continues down to the cellular and molecular level, with cell membranes rupturing as the gravitational gradient pulls the bottom of each cell away from the top. DNA strands stretch and break. Proteins unfold as their complex structures are pulled apart. The entire process from initial discomfort to molecular disintegration would occur in less than a minute. What's particularly disturbing about this process is its inevitability. The same physics applies regardless of what you're made of. If your bones were steel or your skin was carbon fiber, the outcome would be the same, just occurring slightly closer to the black hole. The forces involved exceed the binding strength of any known material in the universe. It's important to note that the severity of spaghettification depends significantly on the black hole's mass. The scenario described above applies specifically to stellar mass black holes, which have a relatively steep gravitational gradient. Supermassive black holes, like the one at the center of our galaxy, present a very different situation. According to NASA calculations, in a supermassive black hole, the tidal acceleration across a human at a distance of 100 kilometers from the event horizon would be 0.00020 cm/sec. This is far less than what a human normally experiences on the surface of Earth. This dramatic difference occurs because supermassive black holes, despite having much stronger gravity overall, have a much gentler gravitational gradient across small distances. Their event horizons are so large that the difference in gravitational pull between your head and feet would be minimal until you're well inside the event horizon. In fact, you might cross the event horizon of a supermassive black hole without feeling any noticeable tidal effects at all. Of course, once inside, other aspects of physics ensure you could never escape. But the immediate experience would be far less violent than approaching a stellar mass black hole. The term spaghettification might sound almost comical for such a violent process, but it accurately describes the physical transformation that occurs. Matter doesn't simply get crushed or compressed near a black hole. It gets stretched into long, thin strands resembling spaghetti noodles. This vivid descriptor has become standard in astronomical literature, though the actual process it describes represents one of the most extreme transformations matter can undergo in our universe. The science behind spaghettification. While this violent transformation of matter has a surprisingly playful name, the science behind it reveals nature at its most extreme. Spaghettification entered scientific discourse through physicist Wolfgang Rendler in the 1950s, but gained widespread recognition when Stephen Hawking featured it in his 1988 bestseller, A Brief History of Time. What's remarkable about spaghettification is how accurately the metaphor captures the physical process. When an object approaches a black hole, it doesn't simply compress or crush as we might intuitively expect. Instead, it elongates dramatically along one axis while compressing along the others. This creates a long, thin strand of material, a shape genuinely reminiscent of a spaghetti noodle. The visual parallel is so precise that even the most rigorous physicists acknowledge it as an appropriate descriptor. While spaghettification dominates popular science discussions, professional astronomers and physicists often use more technical terminology in their research papers. Tidal disruption appears frequently in the scientific literature, particularly when describing stars being torn apart by supermassive black holes. Researchers also refer to the gravitational gradient when discussing the mathematical basis for these effects. The term radial stretching sometimes appears in technical papers, focusing on the directional nature of the deformation. These alternative terms convey the same physical process, but lack the immediate visual clarity of spaghettification. This illustrates an important aspect of scientific communication. Technical precision must sometimes be balanced with conceptual accessibility. In professional journals, physicists might initially use the formal terminology, but often include spaghettification in parentheses or as a secondary reference to ensure clarity. Analogies like spaghettification help us visualize extreme physics that no daily experience can match. The phenomenon represents a perfect case study in how scientific communication bridges technical accuracy and public comprehension. These metaphorical terms create cognitive bridges between abstract concepts and familiar experiences. Some might question whether such colorful terminology diminishes the seriousness of the science it describes. Does spaghettification represent legitimate astrophysics or simply pop science simplification? The answer lies in examining how the scientific community itself uses the term. When a descriptor appears regularly in peer-reviewed journals, scientific textbooks, and NASA technical documents, it has clearly been accepted as valid scientific terminology. The American Astronomical Society, in its journals, regularly publishes research papers referencing spaghettification without qualification or explanation, indicating its status as standard terminology. Similarly, the term appears in graduate-level astrophysics textbooks alongside detailed mathematical treatments of tidal disruption. The scientific community has embraced this vivid terminology precisely because it effectively communicates the physical process. What makes spaghettification particularly valuable is how it combines conceptual accuracy with memorability. The term sticks in the mind, making the underlying physics more accessible to students, science enthusiasts, and even other scientists from different specialties. This accessibility doesn't dilute the science, but amplifies its reach and impact. The phenomenon also demonstrates how theoretical physics predictions can be confirmed through observation. When astronomers observe tidal disruption events, stars being torn apart by black holes, they're seeing spaghettification on a stellar scale. The stretched material forms precisely the elongated streams that the theory predicts, validating both the underlying physics and the aptness of the terminology. This naming convention reflects a broader principle in science. When precise mathematical descriptions become unwieldy for everyday discussion, metaphorical language creates necessary shortcuts. Einstein himself relied heavily on thought experiments and visual metaphors to communicate his revolutionary ideas about relativity. The best scientific communicators recognize that accessibility doesn't compromise accuracy, but complements it. So, why is it called spaghettification rather than something more formally scientific? Because the term perfectly captures the visual reality of the process while remaining memorable enough to aid understanding. The scientific community embraces it because effective communication requires not just precision, but clarity. This whimsical term has earned its place in the lexicon of serious physics by bridging the gap between mathematical formalism and intuitive understanding. While we've examined how this process affects human-scale objects, the most dramatic examples of spaghettification occur on cosmic scales. Stars that venture too close to black holes experience these same tidal forces, but magnified to unimaginable proportions. Unlike thought experiments about human victims, these stellar destructions produce observable evidence that astronomers can actually detect across vast distances. When a star passes too close to a black hole, the same physics we've discussed applies, but on a scale billions of times larger. The star begins to deform with the side closest to the black hole accelerating faster than the far side. This differential pull stretches the star radially while compressing it laterally. As the process continues, the star transforms from a spherical body into an elongated stream of stellar material. Some of this material gets flung outward in spectacular jets, while the rest feeds into the black hole in a process astronomers call accretion. The energy released during these stellar destruction events creates brilliant flashes of radiation across multiple wavelengths. These flares of light serve as cosmic beacons, alerting astronomers to ongoing tidal disruption events throughout the universe. By studying these signals, scientists gain direct observational evidence of spaghettification in action, transforming a theoretical concept into an observable reality. Stars torn apart, observed evidence. These cosmic destruction events aren't just theoretical predictions. They're regularly observed phenomena that astronomers can detect across vast distances. When stars venture too close to supermassive black holes, they experience catastrophic tidal forces that tear them apart in what scientists formally call tidal disruption events, TDEs. These violent encounters provide our most direct evidence of extreme tidal forces in action. A TDE begins when a star's orbit brings it within the tidal radius of a supermassive black hole. This critical distance marks where the black hole's tidal forces become stronger than the star's self-gravity. For a sun-like star approaching a million solar mass black hole, this tidal radius extends to roughly 100 million kilometers, about the distance from Earth to the Sun. What happens next mirrors the spaghettification process we've discussed, but scaled up dramatically. The side of the star closest to the black hole experiences substantially stronger gravity than the far side. This differential force stretches the star along the radial direction while compressing it perpendicular to this axis. The star transforms from a sphere into an elongated ellipsoid, then into a thin stream of stellar material. One of the most thoroughly documented examples occurred in 2019 when astronomers detected a brilliant flash of light from a galaxy approximately 215 million light-years away. This event, designated at 2019 KIS, provided an unprecedented view of a star being torn apart by a supermassive black hole. Using the European Southern Observatory's Very Large Telescope and New Technology Telescope, researchers tracked this event from its earliest stages through the complete destruction of the star. The observations revealed that when a black hole destroys a star, it can launch powerful outward blasts of material that initially obscure our view of the process. Unlike the silent destruction we might imagine, TDEs announce themselves with spectacular electromagnetic flares. As the star's material stretches into a long stream, it follows a range of orbits around the black hole. Some of this material collides with itself, creating shock waves that heat the gas to millions of degrees. This superheated stellar material produces intense radiation across multiple wavelengths. X-rays captured by observatories like Chandra and Newton revealed the hottest regions where material accelerates near the black hole. Ultraviolet and optical light detected by Swift and Hubble telescopes show the broader disruption of stellar material. Radio observations from facilities like the Very Large Array track the outflowing material as it interacts with surrounding gas. Together, these different wavelengths confirm the hot, elongated nature of the stellar debris. The data from these observations confirms several key predictions about spaghettification. First, the timescale matches theoretical models. After initial disruption, the stellar material doesn't immediately fall into the black hole. Instead, it follows a range of elliptical orbits, with material returning to the black hole over weeks and months, creating a sustained feeding process rather than a single catastrophic event. Second, the spectral signatures from these events reveal the chemical composition of the disrupted star. By analyzing the specific wavelengths of light produced during a TDE, astronomers can identify elements present in the star before its destruction. This chemical fingerprinting confirms that the flaring material indeed originated from a torn-apart star rather than from other processes around the black hole. Third, the observed light curves, graphs showing how the brightness changes over time, closely match computer simulations of tidal disruption. The characteristic rise and fall in luminosity follows precisely the pattern predicted by models of stellar material being stretched, heated, and gradually accreted onto the black hole. The frequency of these observations provides insight into how common these catastrophic encounters are in the universe. Current estimates suggest that a typical galaxy experiences a visible tidal disruption event roughly once every 10,000 to 100,000 years. Given that there are billions of galaxies in the observable universe, astronomers detect multiple TDEs each year despite their rarity in any single galaxy. Through careful monitoring of these events, astronomers have created a detailed timeline of stellar destruction. When a star first crosses the tidal radius, the initial stretching begins. Within hours to days, depending on the masses involved, the star elongates dramatically. As it reaches maximum stretching, roughly half the stellar material gets flung outward on hyperbolic trajectories, escaping the black hole entirely. The remaining half becomes bound to the black hole, forming a long stream that begins falling back. This infalling stream doesn't plunge directly into the black hole. Instead, it forms an accretion disk, a flattened, rotating structure of superheated gas. As material in this disk spirals inward, it reaches temperatures of millions of degrees, generating the intense radiation that makes these events visible across billions of light years. The observation of these events confirms a profound reality. Spaghettification isn't just a theoretical concept, but a genuine astronomical phenomenon that shapes our universe. Stars that venture too close to supermassive black holes do indeed stretch and tear apart through exactly the tidal mechanisms predicted by general relativity. Perhaps most significantly, these observations validate the mathematics behind tidal force calculations. The distances at which stars disrupt, the timescales of their destruction, and the energetics of the resulting flares all align with theoretical predictions. This agreement between theory and observation gives astronomers confidence in applying the same principles to understand what would happen to other objects, including planets or hypothetical spacecraft that venture too close to a black hole. While all black holes create tidal forces, the specific effects vary dramatically depending on the black hole's mass. The interaction between a star and a supermassive black hole differs fundamentally from what would happen near a smaller stellar mass black hole. This difference doesn't just affect the timing or intensity of destruction, it completely changes the relationship between spaghettification and the black hole's event horizon. In fact, when it comes to black holes, size matters in a way that produces supermassive versus counterintuitive results. This difference in black hole behavior based on mass creates an unexpected survival paradox. Despite their fearsome reputation, larger black holes actually offer a gentler initial encounter than their smaller counterparts. The mathematics of general relativity reveals that you might survive longer falling into a supermassive black hole than a stellar mass one. The distinction comes down to a fundamental relationship between two crucial distances, the event horizon and what astronomers call the spaghettification radius. The event horizon marks the point of no return, where escape becomes impossible. The spaghettification radius marks where tidal forces grow strong enough to tear matter apart. The relative position of these two boundaries determines whether you'd be destroyed before or after crossing into the black hole's interior. For stellar mass black holes, those with masses between about 3 and 100 times our Sun, the spaghettification radius extends well beyond the event horizon. This means you'd be stretched and torn apart while still able to see the external universe. Your destruction would occur in full view of any observers watching from a safe distance. These relatively small black holes create the most violent spaghettification scenarios. Supermassive black holes tell a different story. These giants, weighing millions or billions of solar masses, have event horizons that extend far beyond their spaghettification radius. This creates an unusual situation where you could cross the point of no return with your body still intact. You'd pass through the event horizon without experiencing extreme tidal forces. The spaghettification would still occur eventually, but only after you've already entered the black hole's interior region. The reason for this difference lies in how these boundaries scale with mass. In bigger black holes, you cross the horizon before being torn apart, because tidal forces at the horizon fall below Earth's gravity. As black hole mass increases, the event horizon grows linearly with mass, but the tidal forces at that boundary decrease dramatically due to the gentler gravitational gradient. we can calculate exactly how different these forces are. For a human falling into a stellar mass black hole of 1 solar mass, the tidal acceleration at the event horizon would reach approximately 19.6 billion meters per second squared, billions of times stronger than Earth's gravity and more than enough to cause immediate destruction. For comparison, a human crossing the event horizon of a 100-million solar mass black hole would experience tidal forces of only about 0.0000019 meters per second squared, thousands of times weaker than what we experience standing on Earth. This creates a remarkable possibility. A human could theoretically cross the event horizon of a supermassive black hole without feeling any noticeable stretching effects at all. You wouldn't be immediately torn apart. In fact, if the black hole were massive enough, you might not notice anything special happening as you cross this supposedly catastrophic boundary. Local physics would continue functioning normally, at least for a while. Of course, this reprieve would be temporary. As you continued falling deeper into the black hole's interior, the tidal forces would steadily increase. Eventually, you would reach the spaghettification radius inside the black hole, and the stretching process would begin. The difference is that no one outside the black hole could observe this destruction. It would occur behind the veil of the event horizon, hidden from the external universe. This creates distinctly different death scenarios between stellar and supermassive black holes. Falling into a stellar mass black hole means experiencing catastrophic structural failure before crossing the event horizon. Your final moments would involve watching the universe around you as your body stretches beyond recognition. Falling into a supermassive black hole offers a different experience. You'd cross the event horizon intact, with no dramatic physical sensations marking the transition. The universe behind you would appear increasingly blue, shifted and compressed into a shrinking circle as light paths bend around the black hole. Ahead, you'd see only darkness. Your destruction would come later, in the isolated realm inside the event horizon, with no possibility of communicating your experience to the outside world. According to NASA's space math calculations, black holes with masses greater than 100 million solar masses create tidal forces at their event horizons that are actually weaker than what we experience on Earth's surface. This means a human could cross this boundary with no physical discomfort whatsoever. The threshold where the spaghettification radius approximately coincides with the event horizon occurs at around 100,000 solar masses. Black holes smaller than this destroy objects before they cross the event horizon, while larger ones allow intact passage across the boundary. Could a human genuinely survive crossing a black hole's event horizon? For supermassive black holes, the answer is technically yes, though survive requires qualification. You would remain physically intact during the crossing, with all biological processes continuing to function normally. However, this survival would be temporary and ultimately meaningless, as destruction inside the black hole becomes inevitable and no information about your experience could ever be communicated back to the outside universe. This counterintuitive relationship between black hole size and survivability reveals something profound about how general relativity works in extreme conditions. The most massive black holes, despite containing the most matter and energy, create the gentlest local conditions near their event horizons. Their gravitational influence extends farther, but the gradient of their gravitational field becomes less steep, reducing the tidal forces that cause spaghettification. This principle applies not just to humans, but to any object approaching a black hole. Stars, planets, and even entire solar systems would experience dramatically different fates depending on the mass of the black hole they encounter. A solar system approaching a stellar mass black hole would be torn apart long before reaching the event horizon. The same solar system approaching a supermassive black hole could cross the event horizon with its planets still orbiting its star, at least temporarily. The fate of larger objects like planets follows these same principles but unfolds on a much grander scale. If Earth were to encounter a black hole, its destruction would follow a precise sequence dictated by the increasing tidal forces as it approached. The process would transform our planet from a stable, life-supporting world into an elongated stream of elemental matter. Earth versus black hole, a planetary destruction. The destruction of a planetary body near a black hole follows the same physical principles we've examined, just scaled to larger dimensions. Rather than focusing on hypothetical scenarios, we can better understand these processes by examining the real stellar disruptions astronomers have documented. When stars are torn apart by black holes, we observe precisely the physics that would apply to any large body. The AT 2019 KISS event mentioned earlier provides a perfect case study. This tidal disruption event, captured in unprecedented detail, showed astronomers exactly how matter behaves when subjected to extreme tidal forces. The process begins at the tidal radius, the distance where the black hole's differential gravitational pull exceeds the object's self-gravity. For stars, this critical boundary typically occurs at distances of millions to billions of kilometers from the black hole, depending on the masses involved. Once crossed, the disruption becomes inevitable. Astronomical observations reveal that the disrupted object doesn't simply vanish. Instead, it transforms into an elongated stream of material that follows a range of orbits around the black hole. This stream doesn't maintain a simple linear shape, but wraps around the black hole as the leading edge completes partial orbits while trailing material is still approaching. The stretched material experiences intense frictional heating as different parts of the stream interact with each other. This heating generates radiation across multiple wavelengths, from radio waves to visible light to X-rays, creating the brilliant flares that alert astronomers to these events. What's particularly noteworthy in these observations is how the material separates based on density. Heavier elements tend to lead the accretion stream, while lighter materials trail behind. This separation occurs because the denser materials experience stronger acceleration from the black hole's gravity relative to their internal forces. Even a large planet would form a long accretion stream similar to stars in TDEs. The primary difference would be the scale and composition of the resulting debris. While stars contain significant hydrogen and helium, planets consist primarily of heavier elements. This compositional difference would affect the spectral signature of the event, potentially allowing astronomers to distinguish between stellar and planetary disruptions if they could observe them. The 2020 observations of at 2019 KISS revealed another important aspect of these disruptions. Not all the material falls directly into the black hole. Some portion, typically 20 to 30% of the original mass, gets accelerated to escape velocity during the disruption process. This material gets flung outward at tremendous speeds, potentially enriching the surrounding interstellar medium with elements from the destroyed object. This ejection of material explains why tidal disruption events often appear as bright flares rather than simple disappearances. The combination of accelerated material, frictional heating, and the formation of accretion structures creates a complex energetic process that releases substantial electromagnetic radiation. For any large body encountering a black hole, the gravitational physics governing tidal destruction is absolute. The process follows predictable stages determined by the increasing tidal forces as the object approaches. The initial elongation, the subsequent streaming of material, and the eventual formation of accretion structures all proceed according to the same physical principles, regardless of whether the victim is a star, a planet, or any other substantial mass. Timescales for these events vary significantly depending on the masses involved. Stellar disruption typically unfolds over weeks to months, the initial breakup occurring relatively quickly, but the accretion of material continuing for an extended period. This extended timeline allows astronomers to observe these events in detail, tracking how the luminosity and spectral characteristics evolve as the disruption progresses. These observations have confirmed several key theoretical predictions about tidal disruptions. First, they verified that the luminosity curves follow the expected pattern with a rapid rise followed by a gradual decline as t-caret minus 5/3, precisely as predicted by theoretical models. Second, they've confirmed that these events produce radiation across multiple wavelengths, with different emission mechanisms dominating at different stages of the disruption. Perhaps most importantly, these observations have demonstrated that matter doesn't simply disappear when it encounters a black hole. Instead, it undergoes a complex transformation process that converts gravitational potential energy into radiation and kinetic energy. This transformation can be so energetic that a single stellar disruption event can temporarily outshine an entire galaxy. The fate of matter after experiencing spaghettification extends beyond the initial stretching and tearing. As the stream of material orbits the black hole, it begins to interact with itself, forming complex structures that astronomers can detect and study. Some of this material will eventually cross the event horizon, while other portions form lasting accretion structures or get ejected entirely. This transformation from cohesive object to elongated stream represents just the beginning of matter's journey near a black hole. The subsequent behavior of this material, how it heats, radiates, circulates, and eventually either falls into the black hole or escapes its influence, reveals even more about the extreme physics at work in these environments. The destruction itself is merely the first step in a complex process that continues long after the original object has lost its identity. Beyond destruction, the accretion process. Once transformed into streams of material, the constituent particles begin a new journey. This transition marks the beginning of the accretion process, a complex dance of matter around the black hole that can last for months or even years. The destruction of matter by a black hole's tidal forces isn't the end of the story, it's merely the beginning of a complex transformation process. When an object undergoes spaghettification, its constituent matter doesn't simply disappear from the universe. Instead, it embarks on one of two possible journeys, either crossing the event horizon into the black hole's interior or becoming part of an extraordinary structure surrounding the black hole known as an accretion disk. An accretion disk forms because matter rarely falls directly into a black hole. Most objects approach black holes with some angular momentum. They're not moving in a perfectly radial path toward the center. This angular momentum prevents matter from falling straight in, much like Earth's orbital velocity prevents it from falling directly into the sun. Instead, the stretched material forms a flattened, rotating disk of gas and dust that orbits the black hole. The formation process begins immediately after spaghettification. As an object stretches into a long stream, different parts follow slightly different orbital paths. These streams intersect and collide with themselves and with other material already orbiting the black hole. These collisions cause the orbits to average out, eventually settling into a disc-shaped structure where everything orbits in roughly the same plane. What makes accretion disks remarkable is their extraordinary temperature. As material in the disk gradually spirals inward, it converts gravitational potential energy into heat through friction. Accretion disks can convert up to 40% of infalling mass to radiation, far surpassing nuclear fusion efficiency, which converts only about 0.7% of mass into energy. This makes them some of the brightest objects in the universe, despite their relatively small size. The disk forms distinct regions with different properties. The inner regions reach temperatures of millions of degrees, producing primarily X-rays and ultraviolet radiation, while the outer regions remain cooler, emitting visible and infrared light. This temperature gradient creates a distinctive spectrum that astronomers can analyze to determine the black hole's mass and accretion rate. Not all material in an accretion disk is destined to cross the event horizon. Some of the most energetic accretion systems produce powerful jets of material perpendicular to the disk. These jets form when magnetic fields threading through the disk channels through the infalling matter and energy outward along the black hole's rotation axis. Material in these jets can accelerate to speed, approaching the speed of light, carrying enormous amounts of energy away from the black hole system and back into the surrounding space. The fate of a specific particle in an accretion disk depends on a complex interplay of forces. Gravity pulls material inward, while rotational forces create outward pressure. Radiation pressure from the intense heat can push material outward, while magnetic fields can channel particles in complex paths. Some particles spiral gradually inward until they cross the event horizon. Others get caught in the magnetic fields and ejected in jets. Still others remain in stable orbits for extended periods before eventually falling in or being blown outward. When a star undergoes spaghettification, its transformation into an accretion disk creates one of the most luminous events in the universe, a tidal disruption event. As this stellar material heats to millions of degrees, it releases an enormous burst of radiation across multiple wavelengths. These events can outshine their entire host galaxy for months. Astronomers have observed dozens of these events, providing direct evidence of the accretion process following spaghettification. The temperature gradient across an accretion disk creates a distinctive spectrum of radiation. By analyzing this spectrum, astronomers can determine the mass of the black hole, the rate at which it's consuming matter, and even details about the original object that was torn apart. One of the most remarkable aspects of accretion is how long the process can take. When a star is torn apart, its material doesn't immediately vanish into the black hole. The accretion process can stretch over months or even years as the stellar material gradually spirals inward. This extended timeline allows astronomers to observe the entire destruction and accretion cycle, gathering valuable data about how matter behaves in these extreme environments. For matter that eventually crosses the event horizon, the journey doesn't end with a dramatic plunge into darkness. According to general relativity, nothing special happens at the event horizon itself from the perspective of the falling matter. The particle continues its inward trajectory, experiencing ever-increasing tidal forces as it approaches the central singularity. Only there, at the singularity, does the mathematics of general relativity predict the complete breakdown of space-time structure. The complete life cycle of matter consumed by a black hole therefore involves multiple transformations, first being stretched into a stream through spaghettification, then joining an accretion disk where it heats to extreme temperatures, and finally either being ejected in jets or crossing the event horizon. This process converts ordinary matter into some of the most energetic forms of radiation in the universe, before some portion eventually disappears from observable reality. This remarkable transformation process represents one of the universe's most efficient energy conversion mechanisms. Through accretion, black holes act not just as cosmic destroyers but as cosmic converters, transforming the potential energy of gravity into radiation that illuminates the surrounding universe. Understanding this complete process presents enormous observational challenges. The regions closest to black holes are difficult to study directly due to their small size and the extreme physics involved. Even our most powerful telescopes can't resolve the detailed structure of most accretion disks. Instead, astronomers must rely on indirect methods, combining observations across multiple wavelengths with sophisticated computer simulations to piece together the complete picture of what happens when matter meets a black hole. This raises a fundamental question. How do astronomers study phenomena they can never directly observe? Seeing the unseeable detection methods. Astronomers have developed sophisticated methods to study these invisible cosmic phenomena despite their inherent observational challenges. When matter undergoes the extreme transformation near black holes, it leaves behind detectable signatures that serve as cosmic evidence. Astronomers detect spaghettification indirectly via TBE flares across X-ray, Chandra, XMM, UV, Swift, Hubble, and radio VLA wavelengths. Simulations on supercomputers then match these flare curves, confirming the physics. This multi-wavelength approach creates a comprehensive picture of the destruction process without directly seeing the stretching itself. The most compelling example comes from observations of at 2019 KISS in 2020, when astronomers documented a star being torn apart by a supermassive black hole 215 million light-years away. This event, captured by the European Southern Observatory's Very Large Telescope and New Technology Telescope, provided unprecedented detail of a TDE from its earliest stages. The observations revealed that when a black hole destroys a star, it can launch powerful outward blasts of material that initially obscure our view of the process. What makes these observations particularly valuable is their distinctive electromagnetic signature. When a star gets torn apart, the resulting material heats to millions of degrees as it forms an accretion disk. This superheated material produces a characteristic pattern of radiation that distinguishes TDEs from other cosmic events like supernovae or active galactic nuclei. The light curve typically shows a rapid increase in brightness, followed by a gradual decline over months as the available stellar material is consumed or ejected. Spectroscopic analysis of this light reveals the chemical composition of the destroyed star. By studying which wavelengths are absorbed or emitted strongly, astronomers can determine if the victim was similar to our sun or a different type of star. This chemical fingerprinting confirms that the observed flares genuinely come from stellar destruction rather than other processes around black holes. The flares from TDEs are extraordinarily powerful, capable of temporarily outshining their entire host galaxy. However, they're often obscured by dust and debris, making them difficult to investigate. The AT 2019 KISS event was particularly valuable because astronomers caught it early enough to observe the outflow of material that created a veil of dust around the black hole. This observation helped explain why some TDEs appear bright in X-rays while others don't. The viewing angle and dust distribution significantly affect what we can detect. Computer simulations fill crucial gaps in our observational data. These simulations use the equations of general relativity to model how material behaves under extreme tidal forces. Starting with a star approaching a black hole with specific properties, the simulations calculate how gravitational forces affect it moment by moment. The results provide visualizations of the stretching process and predictions about what electromagnetic signatures should appear. By comparing simulation results with actual observations, astronomers can refine their understanding of what happens during spaghettification. When a model accurately predicts the observed radiation patterns from a tidal disruption event, it validates the underlying physics and provides confidence that the unobservable parts of the process are also being modeled correctly. The Event Horizon Telescope collaboration has advanced our ability to study black holes by capturing the first direct images of a black hole's shadow and the glowing material circling it. While these images don't show spaghettification directly, they confirm the presence of accretion structures where the final stages of destruction would occur. These images validate decades of theoretical work about how matter behaves in extreme gravitational environments. The timeline of a typical TDE provides crucial information about the physics involved. After initial disruption, the stellar material doesn't immediately vanish into the black hole. Instead, it follows a range of elliptical orbits, with material returning to the black hole over weeks and months. This creates a sustained feeding process rather than a single catastrophic event. By tracking these extended flares, astronomers can test theoretical predictions about how matter circulates near black holes. Future observational capabilities promise to reveal more details about spaghettification. The James Webb Space Telescope will provide unprecedented infrared observations of these events, potentially seeing through the dust that often obscures them. New X-ray observatories with greater sensitivity will detect more distant and fainter tidal disruption events. These new tools will continue to improve our understanding of what happens when matter encounters extreme gravitational forces. The frequency of TDE observations provides insight into how common these catastrophic encounters are in the universe. Current estimates suggest that a typical galaxy experiences a visible tidal disruption event roughly once every 10,000 to 100,000 years. Given that there are billions of galaxies in the observable universe, astronomers detect multiple TDEs each year despite their rarity in any single galaxy. Each new observation adds to our understanding of how matter behaves in the most extreme environments in the universe. By studying the electromagnetic signatures of destruction, astronomers have pieced together a remarkably detailed picture of what happens when objects encounter the overwhelming tidal forces near black holes. Yet for all this progress, a fundamental limitation remains. Our observations can only track matter up to the event horizon, the boundary beyond which nothing, not even light, can escape to reach our telescopes. What happens to spaghettified matter after it crosses this threshold remains in the realm of theoretical physics rather than observational astronomy. At this boundary, our understanding faces its greatest challenge as the laws of physics themselves begin to approach their limits of applicability. Beyond the event horizon lies a realm where our current understanding of physics cannot fully explain what happens to matter. Despite our observational progress, fundamental questions remain about the ultimate fate of material that undergoes spaghettification. The central challenge emerges from a clash between our two most successful physical theories. General relativity predicts infinities at singularities, whereas quantum mechanics forbids information loss, creating the black hole information paradox. This theoretical conflict becomes unavoidable when considering what happens to matter in the final stages of spaghettification. When matter crosses the event horizon and continues its journey toward the center of a black hole, general relativity predicts that tidal forces increase without limit. As the spaghettified material approaches the singularity, the mathematics suggests it would be stretched infinitely thin, a prediction that creates a breakdown in the theory itself. The equations effectively stop working, indicating we've reached the limits of what general relativity can describe. Quantum mechanics introduces additional complications. At microscopic scales, matter exists as discrete quantum particles governed by probability and uncertainty principles. These quantum effects should become significant well before matter reaches the singularity, potentially altering how spaghettification works at the smallest scales. The continuous stretching process described by general relativity must eventually confront the discrete, quantized nature of matter. The information paradox represents one of the most profound unsolved mysteries. Quantum mechanics requires that information about physical systems cannot be destroyed, only transformed. If an object undergoes spaghettification, quantum principles demand that information about its original state must be preserved somehow. Yet general relativity suggests this information becomes irretrievably lost behind the event horizon, effectively erased from the universe. Several theoretical frameworks attempt to resolve these contradictions. String theory proposes that black holes might actually be fuzzballs, quantum objects without true singularities at their centers. In this model, matter undergoing spaghettification would never encounter an infinite stretching force, but would instead interact with a complex quantum state that preserves information. Another prominent approach suggests that information might be encoded in Hawking radiation, the quantum process through which black holes slowly evaporate over time. According to this theory, as a black hole emits radiation, it gradually releases the information of everything that fell into it, preserving quantum consistency but over timescales that could exceed the current age of the universe. The search for a quantum theory of gravity represents one of the most active areas of research in theoretical physics. Such a theory would need to reconcile general relativity with quantum mechanics, providing a complete description of what happens during the final stages of spaghettification. Without this unified framework, we cannot fully trace the journey of matter from its initial stretching to its ultimate fate. At what precise point do quantum effects become significant enough to alter the classical description of tidal stretching? Does matter maintain distinct particle identities all the way to the singularity, or does it transition into some more fundamental form that current physics cannot describe? If information is preserved, exactly how and when is it encoded? The resolution of these questions has implications beyond black holes. The Big Bang Theory, which describes the early universe, also involves conditions where both quantum mechanics and gravity played crucial roles. Understanding what happens to matter during extreme spaghettification might provide insights into the nature of space-time itself and the origin of our universe. For astronomers studying tidal disruption events, these theoretical uncertainties create a boundary to their understanding. Observations can track the initial stretching of stars and the formation of accretion disks, but the final fate of matter that crosses the event horizon remains in the realm of theoretical physics rather than observational astronomy. What makes these unsolved mysteries particularly significant is that they represent more than just gaps in our knowledge. They highlight fundamental inconsistencies in our current understanding of physics. The process of spaghettification begins with well-understood gravitational forces but ends somewhere beyond our theoretical grasp, challenging our most basic understanding of how reality works. The mysteries surrounding spaghettification and black hole interiors represent the frontier of fundamental physics. If we could fully understand what happens to matter as it undergoes extreme stretching near a singularity, we might uncover the key to unifying quantum mechanics and general relativity. a breakthrough that would transform our understanding of the universe. These theoretical puzzles contribute to what makes black holes so fascinating yet disturbing. While other cosmic phenomena can be destructive, most operate according to well-understood physical principles. Spaghettification, however, leads directly to a place where our best theories of reality break down, creating a unique kind of scientific uncertainty that borders on the existential. Among all the destructive forces in the cosmos, spaghettification stands apart not just for its physical violence, but for how it challenges our fundamental understanding of reality itself. This combination of physical extremity and theoretical mystery gives black holes a special place in our cosmic imagination. Cosmic horror, the existential implications. Beyond the theoretical mysteries, black holes and spaghettification have profound implications for how we understand our place in the cosmos. The physical reality of these phenomena forces us to confront uncomfortable truths about existence itself. Among all cosmic phenomena, spaghettification stands apart in the specific kind of unease it creates. Supernovae explode with unimaginable force. Gamma-ray bursts sterilize vast regions of space, and neutron-star collisions generate gravitational waves that ripple through space-time. Yet these events, despite their violence, represent transformations rather than absolute destruction. A supernova scatters a star's elements into space, seeding future generations of stars and planets. Even in destruction, structure persists, and matter continues in new forms. Spaghettification offers no such continuity. When an object undergoes this process, the outcome isn't transformation, but reduction, a complete breakdown to fundamental particles that disappears behind an event horizon. Nothing recognizable remains. The object doesn't become something else. It ceases to exist in any meaningful sense within our observable universe. This fundamental difference creates a distinct existential discomfort. Most cosmic processes, however violent, maintain some connection to the physical laws we understand. Matter changes form, but follows predictable patterns. Black holes represent regions where familiar physics approaches its limits, and the most basic structures of matter cannot maintain integrity. The universality of spaghettification adds another dimension to its unsettling nature. No material, regardless of its strength or composition, can resist these tidal forces once they exceed atomic binding energies. Diamond, tungsten, neutronium, the strongest substances imaginable, would stretch just the same. This suggests something profound about reality. All structure in our universe exists conditionally, maintained by a balance of forces that black holes can overwhelm. The manner of destruction itself carries particular psychological weight. Unlike radiation, which might kill instantly, spaghettification progressively dismantles physical structure. The body elongates, tissues separate, organs pull apart, cell membranes rupture, and eventually even atoms distort. This gradual unraveling of physical form represents a complete dissolution of structure that feels fundamentally different from other cosmic hazards. Time dilation effects near black holes add another layer of existential strangeness. From an outside observer's perspective, an object falling toward a black hole appears to slow down, eventually freezing at the event horizon. Yet from the perspective of the falling object, time continues normally as it crosses the horizon and meets its destruction. This relativity of experience challenges our intuitive understanding of time as a universal constant. What makes black holes particularly significant is how they reveal the conditional nature of physical reality. We typically perceive solid objects as fundamentally solid, but extreme tidal forces reveal this perception as incomplete. At a fundamental level, all matter consists of mostly empty space with particles held in relationship by forces that extreme gravity can disrupt. This realization extends beyond astronomy into questions about the nature of existence itself. The study of spaghettification also highlights the limits of human comprehension. When scientists trace the path of stretched matter, they reach a point where current physics cannot provide definitive answers. What happens at the singularity? How do quantum effects modify the stretching process at microscopic scales? These questions mark the boundaries of current knowledge, creating a kind of intellectual vertigo, the awareness that reality extends beyond our capacity to fully comprehend it. Perhaps most significantly, spaghettification reminds us that our universe operates by laws that can destroy form and defy intuition, reinforcing our drive to understand gravity's ultimate frontier. The phenomenon represents not just a physical process, but a profound reminder of how the universe can operate in ways fundamentally alien to human experience and intuition. This alien quality is precisely what makes black holes objects of both scientific fascination and existential contemplation. They operate according to principles that, while mathematically describable, create conditions unlike anything in ordinary experience. The extreme physics at work near black holes, where space and time themselves distort, represents a fundamental alienness that distinguishes black holes from other natural phenomena. Many astronomers acknowledge a particular fascination with spaghettification precisely because it makes them uncomfortable. The phenomenon begins with standard gravitational concepts, but ends somewhere beyond current scientific understanding. This transition from the comprehensible to the incomprehensible creates a unique kind of scientific wonder, one tinged with the recognition of how much remains unknown. In confronting these realities, we gain perspective on our existence. The same fundamental forces that allow complex structures like stars, planets, and living organisms to form also contain within them the potential for complete structural dissolution. Spaghettification represents this ultimate power of gravity, a reminder that even the most fundamental structures in nature exist within physical constraints that can be exceeded. As we continue to study these phenomena, we push against the boundaries of our understanding, driven by the human need to comprehend even the most extreme aspects of reality. The fact that we can mathematically describe and predict spaghettification, even if we cannot fully explain what happens at its conclusion, represents a remarkable achievement of human intellect in the face of cosmic mystery. Our journey through the physics of black holes has taken us from the initial tidal forces that begin stretching matter through the complete spaghettification process to the formation of accretion disks, and finally to the mysteries that remain at the singularity. Black holes reveal gravity at its most extreme, a force capable of reducing any object to elementary particles. This isn't merely destruction, but complete structural dismantling, where the strongest materials in existence stretch into atomic streams. Though we cannot directly observe what happens beyond an event horizon, spaghettification provides a unique window into extreme physics. The process begins with well-understood tidal forces, but leads to regions where our current theories break down. As we continue probing black holes, each shredded star brings us closer to grasping the universe's deepest secrets. Like and subscribe for more cosmic frontiers.